Okay, so students, welcome to this next edition of our revision lectures in class 11 physics. So today we will be continuing ahead with the topic of system of particles or center of mass, which we've been doing in the last two lectures. Let's move on ahead. So this is session number 4 of system of particles, and we will be exploring the aspect of collisions in a very detailed fashion in today's lecture. Because it's a very important part of this section, as well as it's important from the point of view of weightage and competitive exams, especially the JEE Mains and JEE Advanced. Collisions is a very important part of it. So let's get down to it and understand how we apply the principles of conservation of linear momentum, among other things, in the applications in collisions. Now, just one aspect to tell you about before we get into the equations, etc., is that in this particular section, we will be looking at collisions between particles or even collisions between bodies where there is transfer of only linear momentum. We will not be looking at situations where there is collision and as a result of that, there is transfer of angular momentum. That will come in a different situation of, conservation of angular momentum and rotational dynamics, and those type of collisions will come in that section of our physics syllabus. So just to make that point clear. Right, so moving ahead, let's discuss the different types of collisions that come within this section of system of particles. So the first and the most simple type of collision is what we call the head-on or one-dimensional collision. So these type of collisions, as you know, are classified by the fact that the initial momenta or the initial momentum vectors of the two particles which are colliding and the collisional impulse vectors all lie among a common axis, and therefore final momenta after the impact also lie along this common axis of impact. So that's why it is called head-on or one-dimensional collisions. So let's try to understand visually some particular cases of this. So for example, if we have two particles that are moving such that, so let's say this is particle A and this is particle B, and they are initially moving such that their velocity vectors are lying along the particle to particle line. So both these initial velocity vectors you can see are lying UA and UB. They're lying along this common axis. That fulfills the first part of our statement, that the initial momenta along the common axis. Then what happens is after a bit of time, let's say they collide somewhere over here because B is moving slower than A. So eventually A catches up with B, but by the time B has moved a bit further. So when they collide, the collision impulse that acts like this. This is the impulse on B because of A. This is the impulse on E because of B. And that acts like this. And that also lies along that common axis, which is the line of impact or the axis of impact. And as a result of that, immediately after the impact, E and B might have momenta which are vectors, let's say like this. Which are also along that common axis. Let's say B has increased its magnitude of velocity along the same axis, whereas A has actually recoiled back. Because of the impact impulse, A is actually now returning back or recoiling back with the final velocity B, and B is continuing forward with the final velocity B. So you can see that all the vectors, the initial momenta, the collision impulses J, and the final momenta M into VA and whatever mass would be into VB, they're all lying out along this common axis. This is the line of impact axis. So all of them are lying along this common axis. So it is what we classify as a one-dimensional collision. And the condition for particles to have a one-dimensional collision is that the initial velocity vectors should be along the line joining the two particles. Okay, so this example, two particles colliding such that their initial velocities UA and UB are along the line joining their positions. Okay. So they are along the line of their relative position with respect to each other. That could be one situation in which we experience this head-on or one-dimensional impact. Another very simple situation where something like this could happen is, for example, you could have a situation where you have some kind of a surface, and on that you have cubical or cuboidal blocks which are moving. And let's just say over here we've selected a situation where they are moving towards each other with initial velocities UA and UB. Like this. So here also what will happen is that during the impact, because the floor is supporting them, so their line of motion will remain along the horizontal plane, and they will be applying impulse on each other in this sort of manner. This is the impulse on A because of B. This is the impulse on B because of B. And as a result of that, after the impact is over, they will still continue along the same axis. So once again, we can see that their final velocities. Now let's just say for argument's sake that this continues in the same direction. But basically, again, there is a common axis. Okay, so the initial momenta, the final momenta, and the impulses, the collision impulses, they're all along the common axis, or they're along the line of impact. So this is also an example of a one-dimensional collision. Yet another example of a one-dimensional collision would be a situation where, now this example is going to serve us a couple of purposes, apart from just the fact that we'll see the condition for the collision to be one-dimensional. Now suppose we have two disks which are in a horizontal plane. So disk A and disk B. And these are their centers. Therefore, this is the line joining their centers. Now, suppose disk B is at rest, but disk A is moving with an initial velocity, which is directed like this. So the velocity vector of velocity or momentum vector of this is along the center to center line. So then what will happen is when they do come in contact, when A and B come in contact, it will be like this. The center to center line will be the line along which the collision impulse is acting. That's why after the impact, the final velocities will also be along the same center to center line. So you can see the line of impact will be basically the center to center line, because these are two round bodies, like two discs, or they can even be two spherical bodies on a horizontal plane or whatever. So in that case, it will be like this. And because the initial momentum of the particle colliding with the other one which is stationary, or the initial momentum of the disk or sphere or whatever colliding with the stationary one is along that center to center line of impact. So that's why what will happen here is that again the final moment after the impact will also be along the same axis. It will be along that center to center axis. So after the impact, this will have gained a velocity in this direction, and let's say this would have slowed down from its initial velocity, or it can even recoil. But whatever happens, the velocity vectors will be along this axis, along the line of impact. So this is again an example of a 1D collision. But now visualize the situation where the same two round objects, like the two discs, are having a slightly different kind of collision, where let's say this is one of them and this is the other one. Now in this case, let's just say that suppose the situation is like this, that the initial velocity of this one is a vector along an axis which doesn't quite pass through the center of the second one, because the center of the second one is here and the center of the first one is here. So you can see that A and B's center to center line is actually this one, but the initial momentum of A is not along that one and B is at rest. So now what will happen here is that when they do come in contact, so in this example, when they do come in contact, the line of impact will not be the same as the line of the initial moment. So the collision impulse that is acting on the mutual collision impulse that they apply on each other, that will be along the line of impact, which will be along the center to center line. So that line will be this one over here, which I'm drawing next. So this is, let's say, the center to center line. So what will happen is that as they collide, the impulse they apply on each other will be along this line. This one will experience an impulse in this direction backwards. And this one will experience an impulse in this direction forward. So this will be the axis of impulse on B because of A. And this will be the direction of impulse on A because of B. So you can see that that is along the line of impact, or the axis of impact, which is the center to center line. Okay. But the initial velocity of A, as you can see, was not along that direction. That was along this direction. So what's going to happen is, as a result of this now, A and B are not going to have the common direction of motion after impact. They're going to have different directions of motion. So what will happen immediately after impact is that B will go off with a velocity along this center to center line, but A will go off with a velocity in some sort of direction like this. So this becomes an example of a two-dimensional collision, because the momentum vectors immediately after the impact represent two-dimensional vectors. They're not along one common axis. So this is the distinguishing factor between one-dimensional collisions and two-dimensional collisions, and we'll talk about them in more detail as we go along in today's lecture. So let's start with the full detailed mathematical analysis of one-dimensional or head-on collisions. So head-on or one-dimensional collisions in detail. Okay. So we take a sort of generalized situation where the two colliding bodies or particles are of masses m1 and m2, their initial velocity vectors along their axis of impact or along the line of impact are u1 and u2. Okay. So you can see also here that the approach velocity, that is the approach velocity of particle m1 with respect to particle m2. M1 is approaching m2 at a certain rate, and that is equal to u1 minus u. Now, as they come in contact, as we've discussed, they will apply equal and opposite collision impulse on each other. So, by Newton's third law, force acting on particle 2 because of 1, and therefore impulse on 2 because of 1 will be equal and opposite to the impulse on 1 because of 2. Action reaction pair. So this is what tells us that for the system of particles m1 plus m2, linear momentum is conserved. For the system, the linear momentum is conserved. So immediately after impact, what happens is that, let us say, the two particles have individual velocity vectors, which are like this for A and like this for the second one. So this is V2 for the particle of mass m2, and this is V1 for the particle of mass m1. Okay. So the first equation we'll be able to write here is the conservation of linear momentum, which ideally we want to write like this, that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. But since the direction of all four vectors is along the same axis over here, okay, so we can reduce this to a one-dimensional equation. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Before we proceed further, you can see another point here, that after the impact, the separation velocity between the two particles, that becomes, according to the direction of vectors I've taken over here, that becomes v2 minus v1. This is the separation velocity of m2 with respect to m. So that becomes like this. Okay, so the momentum conservation equation becomes the first equation that we can write by application of mechanics concepts over here. Now, the second thing is, if the collision is, in addition to being one-dimensional or head-on, if the collision is also elastic, or what we call perfectly elastic, that means kinetic energy is conserved. So, perfectly elastic, and the total kinetic energy of the colliding particles or bodies before and after impact is conserved. So in other words, it means that the materials of the bodies are elastic, which means that during the impact they store elastic potential energy, and then that elastic potential energy, as the impact is coming to an end, as the interaction is coming to an end, is reconverted into kinetic energy without any dissipation. So for that situation, the initial kinetic energy is the initial kinetic energy before impact is equal to the final kinetic energy after impact. So this becomes our second equation. Now it's a matter of, suppose we are given the values of M1, M2 and U1 and U2, how we can solve for V1 and V2. So let's look at that. So the first equation can be rearranged and written in this way, that M1 into U1 minus V1 is equal to M2 into V2 minus, and the second equation similarly can be rearranged and written like this, that M1 into U1 square minus V1 square is equal to M2 into V2 square minus U2 square. So if we rearrange these two equations and write them in this way, and now just divide equation 2 by equation 1, we'll get the relation that U1 plus V1 will become V2 plus U, or U1 minus U2 is equal to V2 minus V1, which shows us that the approach velocity is equal to the separation velocity. Okay. So that becomes an important property of the perfectly elastic collision. In a perfectly elastic collision, in a head-on perfectly elastic collision, the approach velocity is equal to the separation velocity. Okay. And now, of course, solving this as a system, solving these, we get these sort of relations for V1 and V2. So these are the generic values of V1 and V2 in terms of U1, U2 and their masses, which we can generate from the above conditions of the collision being head-on as well as perfectly elastic. Now we can look at certain interpretations of this. For example, but before that, let's start with a numerical example of this application. So let's look at a situation like this, that we have a particle of mass 2 kilograms and another particle of mass 3 kilograms, and they are initially moving towards each other. With a velocity of 1 meter per second and 1 meter per second. So we want to find the final velocities after impact, and we want to find the impulse on impact. What kind of impulse they apply each other? They apply on each other. Okay. I'll just give you a minute to analyze this question and try and work it out, and then we'll discuss this further. Okay, so let's understand this question by various different methods. One is we can directly use the formula. So you can see that it's given to us that M1 is equal to 2 kgs. U1 is plus 1 according to the direction. M2 is 3 kgs, but U2 is equal to minus 1 according to the directions. So now using the formula from above, V1 should be this. Okay. This is of course assume the collision is head on and perfectly elastic. So with that assumption, we can use these formulas. So this becomes the final velocity of the first particle becomes this much, and the final velocity of the second particle will become so substituting the values. Okay, so our second particle's velocity is becoming plus 0.6 meters per second. So let us interpret this result that we get. So I'll just give you a minute to go through this first. Okay, so if we have to just interpret this result, what it's telling us is that the 2 kg particle moving at 1 meter per second directly towards a 3 kg particle which is coming towards it at 1 meter per second. So you can see one thing, that the approach velocity is 2 meters per second, and you can see that the momentum of the system is, so with our sign convention of this being the positive direction, it is minus 1 kg meter per second. So now this is before impact, of course, and after impact, you can see that what's happening is that the 2 kg particle is having a final velocity of minus 1.4, so 1.4 meters per second backwards, and the 3 kg particle is having a forward velocity of 0.6 meters per second. So you can see that the separation velocity is equal to 1.4 plus 0.6, that is equal to 2 meters per second. So connecting these two, you can see that as expected, we have got that approach velocity is equal to separation velocity because it is a perfectly elastic collision, which basically just confirms for us that the application of the formula is correct, because the derivation of the formula in the first place involved the condition that approach velocity is equal to separation velocity when the collision is perfectly elastic. So it has to be the case. So we're just confirming that the result we have got agrees with that part of the derivation. The second thing we can see that the momentum of the system after the impact is minus 2.8 for this one, plus 1.8 for that one. So that is again plus, that's again minus 1 kilogram meter per second. So now if we connect this and this, we can see that the initial momentum is equal to the final momentum for the system, which again is in agreement with the the derivational principle that if the collision is perfectly elastic, then the momentum of the system before and after is conserved. And similarly, we can also check that the kinetic energy is conserved. You can also see that the initial kinetic energy of the system was half into 2 into 1 square. Plus half into 3 into 1 square. So that's 1 plus 3 by 2 or 2.5 joules. Now the final kinetic energy after impact, you can see is half into 2 into 1.4 square plus half into 3 into 0.6 square. Okay. So if you work this out, you can see you will get you get 1.96 here plus 3 by 2 into 0.36. So that would be so you can see that that is also 2.5 joules. So once again, if you connect these two, you can see that kinetic energy is conserved. So all the three properties of the perfectly elastic head-on collision are getting satisfied by this. And see this way. Now there's another way in which we can do this question more conveniently. Sometimes using the formula is not after all the shortest way of doing the question. Let's see how. So you can also do this logically or using properties of the head-on perfectly elastic collision. So that is like this, that before impact, the velocity is being like this. We can see that the approach velocity is equal to 2 meters per second. So let us assume that after impact, the 3 kg particle has some velocity v2. Okay, and let's assume that this particle, the 2 kg particle, has a velocity of v1. So we know that the separation velocity is equal to v2 minus v1. And that should be equal to the approach velocity because it's a perfectly elastic collision. So we can see that v2 minus v1 should be equal to 2, or we can say that v2 is equal to v1 plus 2. So that becomes our first equation. And then we can say that, okay, momentum is conserved. So conservation of momentum will show us that 2 into minus 1 plus 3 into, sorry, 2 into 1 plus 1 plus 3 into minus 1 should be equal to 2v1 plus 3v2. So that becomes our second equation. 2v1 plus 3v2 should be equal to minus 1. And in this, if we just substitute this, so we can see that 2v1 plus 3 into v1 plus 2 is equal to minus 1. We get 5v1 is equal to minus 1 minus 5. So minus 1 minus 6. Okay, so v1 we can see is v2 being v1 plus 2 becomes plus 0.6. So that's another way in which we can approach a problem like this. Now another very important aspect about perfectly elastic head-on collision that we learn. Okay, we've already seen the formula. You've already seen these formulas. So now, if m1 is equal to m2, that is, the colliding particles are of identical mass. Okay, then, as you can see from the above formula, these two terms will become zero if m1 is equal to m2. These two terms will become zero, and these two terms will become unity. It will become one. So we can see that if masses are equal for the two colliding particles, v1 will become u2 and v2 is equal to u1. So that means the colliding particles exchange velocities, okay, momenta, and even kinetic energies. They exchange each other's values. So this is a very important special case to remember, especially when we are dealing with questions at the competitive exam level. So, for example, if we see a situation where something like this is happening, a particle of mass m moving with v naught, initial velocity, comes and hits another particle at rest, and is given to us that the collision is perfectly elastic and head-on. Then we'll know that immediately after impact, suppose these are particles A and B, then immediately after impact, the particle B will have the velocity v naught, and the particle A would have come to rest, because v1 becomes u2, which was 0, and v2 becomes u1, which was 0. Exchange velocities or momentum, kinetic energy. Or for example, we have a situation where particles of identical mass are approaching each other from opposite directions, okay, like this, and it's a perfectly elastic head-on collision. Then we know that after impact, what will happen is that A will recoil back with 1 meter per second, and B will again reverse its direction. So U1 was plus 3, U2 was minus 1. Okay. M1 is equal to M2, and the collision is head-on perfectly elastic. So that means so they exchange momenta, velocities, or kinetic energy, and all these things. So this becomes an important aspect. Next up, we'll see another important special case of perfectly elastic head-on collision. So if we have a particle of mass m1, which is moving with some velocity u, and it makes a head-on elastic collision with another body which is at rest. So it's a head-on perfectly elastic collision again. So what will happen here is that if m1 is greater than m2, that is, the colliding particle is heavier, then m1 slows down, but continuing in the same direction. Okay, because by formula you can see that v1 is m1 minus m2 upon m1 plus m2 into u, and v2 is 2m1 upon m1 plus m2 into u. Okay. So this becomes like 1 minus m2 by m1 upon 1 plus m2 by m1. So you can see that what is happening is that v1 is positive because m1 is greater than m2, but v1 is less than u. And this we can write as you can see that v2 is greater than. So the second particle, which is lighter, will pick up a speed more than the initial speed of the first particle, and the first particle will just slow down, continuing to move in the same direction. Because on the other hand, if m2 is greater than m1, then what happens is that v1, which is m1 minus m2 upon m1 plus m2 into u, v1 becomes negative. So the first particle recoils. So if it's a lighter particle, it goes and collides with a heavier particle at rest, then immediately after impact, the first particle will definitely recoil. It will have a v1 which is backwards in direction, and the second particle will have a v2 which is less than. So this is again something that we can sort of gain a feel for in terms of how the ratio of the masses, whether the first one is lighter or heavier, is going to affect whether it recoils or continues in the same direction. and whether the second one picks up a larger magnitude of velocity or a lesser magnitude of velocity. Of course, in the event of the collision being perfectly elastic and head-on. Okay. Now, moving on, let us look at a situation where we are looking at head-on or one-dimensional collisions. That are partially inelastic. So you'll understand in a bit what we mean by the term partially inelastic. So the term partially elastic means that there is loss or dissipation of kinetic energy during the collision. And this happens due to non-conservative inelastic forces or impulses which act between the bodies which are colliding. What these tend to do is that kinetic energy or a fraction of the kinetic energy is dissipated into other forms of energy. Heat, sound, if there's sparking, light, etc. So what we'll also understand that when this happens, we'll also be able to show that the separation velocity is always less than the approach velocity. Okay. However, in a partially inelastic collision, the separation velocity is not equal to zero. That means that the particles do not stick together. When they stick together, it is called a perfectly inelastic collision and not a partially inelastic collision. Okay. So let's understand here what's happening. Going back to our earlier scheme, if two particles moving like this are making a head-on impact, but such that after the impact, the kinetic energy is dissipated by a certain amount. So you can see that m1u1 plus m2u2 is equal to m1v1 plus m2v2. That is, there is conservation of linear momentum. But at the same time, half m1u1 square plus half m2u2 square is greater than half m1v1 square plus half m2v2 square. So there is dissipation of kinetic energy. Okay. So solving it in the same way, what we'll be able to work out is that compare this equation with the second one, but now the second one has an inequality. It's greater than. So by dividing the two equations, what we this time get is that u1 plus v1 is greater than v2 plus u1, or u1 minus u2 is greater than v2 minus v1, which basically tells us that the approach velocity is greater than the separation velocity. So to express this better, what we do is we define the coefficient of restitution, which is a dimensionless coefficient denoted by the symbol E. This is defined by separation velocity's ratio with respect to approach velocity, or v2 minus v1 upon u1 minus u2 in our diagram above. So for a partially inelastic collision, the coefficient of restitution is greater than 0 but less than 1. Greater than 0 because V separation is not equal to 0. But less than 1 because V separation is less than 0. So that particular parameter is called the coefficient of restitution. So let us understand this with another example. So now suppose we have a situation where a particle of mass m moving at a velocity v naught makes a head-on partially inelastic collision such that there is 25% loss in kinetic energy for the system of particles here. For that system, there's a 25% loss in kinetic energy. So we want to find the final velocities and we want to find E, that is the coefficient of restitution. We know that E will be between 0 and 1, but how much it will be, we want to find that out. Okay, so let's look at this question. Okay, so let's understand this question next. So in this, there are a couple of approaches by which we can do the question, and one of the approaches is like this: that suppose we assume some coefficient of restitution. Let E is equal to velocity of separation divided by velocity of approach. So let's assume that after impact, A and B have some velocities v1 and v2 like this. So v2 minus v1 upon approach velocity, which you can see in the above diagram, is v0 is equal to E. Okay, so from this we can see that v2 is equal to v1 plus ev. That's our first equation, and we can see that momentum conservation will tell us that mv0, or rather mv1 plus mv2 is equal to mv0. This is conservation of linear momentum. So cancelling of the masses, we can see that v1 plus v2 is equal to v0. That's a second equation. So according to this, v2 is equal to v0 minus v1. So if you compare the first two equations, this and this, so you can see that v1 plus v0 has to be equal to v0 minus v1. So from this we can write 1 plus 1 v1 is equal to 1 minus e v0. So we can substitute the value of v1 as 1 minus e by 2 v0, and therefore v2 will become so v2 can be substituted as 1 plus e by 2. So we have got v1 and v2 in terms of this unknown quantity e, which is the coefficient of restitution, where we understand e is between 0 and 1. Now we use the fact that there's 25% loss of kinetic energy. So that means the final kinetic energy must be equal to 75% of the initial kinetic energy, because there's a loss of 25%. So that means half m v1 square plus half m v2 square should be equal to 0.75 times half m v0 square, or v1 square plus v2 square is equal to 0.75 v0 square. So from this we can just substitute these values in terms of the coefficient of restitution. So this was 1 minus e by 2 1 plus e by 2. So we can see that this will become 1 minus e whole square plus 1 plus e whole square divided by 4 is equal to 0.75, or e square will become half, or e is equal to 1 by root 2, or approximately 0.7. And from that we can see that v1 is equal to v1 is 1 minus e by 2. And v2 is and the coefficient of restitution is about 0.7. So that's one approach for doing this question. Another way of approaching the same question would be, let's say, something more direct, where you would say that we start with the conservation of momentum and the equation for energy that is given. So we have this is our first equation, and final kinetic energy is 75% or 0.75 times the initial kinetic energy. So these become our two equations, and we substitute this information here. So we get this sort of a quadratic relation. From this, we get the possible values of V1, and as you can see, they are so V1 being this, we'll take the smaller value to be V1, so that will become so from this we can see that the smaller of the two roots will be the value of V1, and the larger of the two roots will be the value of V2. Where we are taking 1 by root 2 as approximately 0.7. And from this we can also see that the separation velocity, which is V2 minus V1, is 0.7 times V0. So the ratio of separation to approach velocity and that is nothing but the coefficient of restitution. So 1 by root 2 or 0.7, that is the coefficient of restitution. So this becomes another way of approaching this type of problems. All right, so with this we conclude today's session, and the next lecture we will take up more examples of collisions and more types of collisions, including oblique collisions between particles and collisions of particles with rigid surfaces, etc. So wish you all the best until then, and see you next time.